Hello, everyone. Today's going to be a short presentation. We're going to be focusing on optics. We start off quickly with a quick discussion on reflection, just as a reminder. So reflection, as we're aware of, light hits an object and it bounces off of it, and then it travels. That reflection is what allows us to see objects. In order for us to see something, light has to hit it and then bounce back and reach our eye. That's how we perceive it, and that's how we know something is there. Reflection happens when light strikes an object, and usually the angle that it bounces off of is dependent upon the surface. If the surface is smooth, then the angle of incidence, or in other words, the angle coming in, is going to be the same as the angle of reflection or the angle coming out if the surface is perfectly flat in the case of a mirror. Okay, so the angle bouncing is going to bounce off perfectly if it's a smooth surface. If it is not a smooth surface, then you get stuff like this. And as we talked about before, this is how you make that privacy glass. The light scatters in all different directions, so you cannot get a clear image if we're referring to mirrors, okay, in windows. Okay, so this is what you get: perfect bounces and scattered. If it's scattered, the image becomes blurry. What I want to focus on here is this new idea of there's virtual images and there's real images. Okay, so when it comes to mirrors and optics, you're going to see these terms. You're going to see them in the next couple slides: real and virtual. A virtual image means that it looks like the image is behind the mirror. When you look in the mirror, that's exactly what it looks like. It looks like you are like inside of the mirror, behind the mirror. We know that's not true because there's nothing behind the mirror. The mirror is just a surface. There is no other world behind it, but that's what it looks like. And when that happens, we call that a virtual image. Okay? Pardon me, getting a phone call. Okay, I am back. Yeah, virtual image just means the image, it appears to be behind the mirror. Okay, now that's not always going to be the case. If you had a real image means it looks like it's in front of the mirror. And that may sound weird and strange, but we'll get into how that's possible in a second. Okay, that happens with spherical mirrors. Okay, I don't know if you've ever been to any of those places that have those like weird, oddly shaped mirrors that you can like play around with and you see like different deformed objects and stuff. But this is where you get those kind of images. All a spherical mirror means is that it's a curved mirror. Okay, it follows a radius kind of like a sphere. It's a curved mirror. Okay, that's all that means. If the curve is on the inside, okay, by inside I mean, let's see, what's the weirdest way to describe it? Yeah, inside. Okay, if it's inside, then it's concave. Okay, so this left side, this is concave. So like imagine if we were to finish drawing this sphere. Obviously that's not pretty, but the rays are inside the sphere. Okay, so this is concave. If the rays are on the outside of the sphere, we call that convex. Okay, so this is a concave mirror and this is a convex mirror. And you're going to get different images depending on what type you have. Okay, so let's get into that. Now, for the purpose of this, we're going to make the assumption that all light coming in is parallel. If you notice here, we're drawing all the lines in a straight line. Normally, you have light coming in from all different directions. But we're going to assume that if a ray is coming from something far away enough, all the lines are going to appear to be parallel. Okay, that's the assumption we're making, that we're working with all parallel lines. All right? Okay. So when light bounces off of the concave mirror, okay, concave is the one where it's inside. When all light bounces off a concave, they tend to travel to a specific point. And that specific point, we call that the focal point. But if the curvature is too large, they don't all necessarily align at the same point. Okay, notice how some converge here and some converge here. But if the curvature is small enough, you get them all to cross at the same point. And this point is called the focal point. Okay, F stands for focal point. Okay. The C stands for the center of curvature. Okay. So if you were to finish, again, if you were, imagine this, we finished drawing this sphere, C would be the middle of that sphere, okay? So that's what the C and F stand for, okay? That's what the C and F stand for. If you wanted to calculate what the focal point was, like if you didn't know where it would be, if you know what the radius of the sphere is, okay, and the radius would just be from the wall to the center, okay, that's why they have it labeled here R. If you know the radius, then the focal point is going to be half of it, okay? That's how you find the focal point for a mirror, okay? This section I'm going to skip. This is about how to figure out what type of image you're going to get, but skip this section and we'll get to just the summary, okay? I'm not worried about these equations because things get complicated. But what I want you to know is this, starting from here. If the object, so if you're standing in front of this mirror, if you're between the center of the sphere and the focal point, if you're in between it, the image you're going to get is going to be real, meaning that it's going to appear to be in front of the mirror, not behind it, and it's going to be inverted, okay? Meaning it's going to appear to be upside down. So if you were to place an object between the center and the focal point in front of this mirror, you're going to get a new image that's going to make it look upside down. And it's going to be larger. Magnified means larger, okay? So these are the terms you're going to see a lot, okay? You're going to see virtual or real, you're going to see magnified or demagnified, and you're going to see inverted or not inverted, okay? If it's inverted, it just means it's upside down. So this is the first one, okay? If you're standing in the middle of the center point and the focal point, you get a new image that is larger, it's real, and it's upside down. If you are behind the point of curvature, okay, so if you're behind C, if you're here on the left side of C, the image is going to look smaller. It's going to be real, meaning it's going to be in front of you, and it's going to be inverted, which means it's going to be upside down. Okay, so this is the second one. Okay. The third one is if you're inside the focal point. So if you're past the focal point, if you're super close to the mirror, you're going to get an image that is magnified, meaning it's larger. It's going to be virtual, which means it's going to appear like it's behind the mirror, like you're used to. And then it's going to be upright, meaning it's not going to be upside down, okay? So if you yourself were to go to one of these, usually they're at like playhouses or like circus type places, and they have one of these mirrors. If you stand in front of it, you're going to get an image that makes you look super tall, and it's going to be zoomed in, and it's going to be virtual, meaning it's going to be like behind the mirror like you're used to, okay? That's for concave. And I believe those are the three. You're either behind the center point, in between, or you're in front of the focal point. If you're behind the center point, again, you're going to look, okay, this was the second one. If you're behind the center point, you're going to get smaller and you're going to be upside down, but it's going to be real. If you're in the middle, you're going to get larger, it's going to be real, and it's going to be upside down again. And then the third one is if you're past it, it's going to be virtual, you're going to be taller, and it's going to be upright. Now we're switching to convex. Convex meaning the light is on the outside of the sphere. This one's going to be a little different. Okay. There's only one option for this. When you stand in front of a convex mirror, the image is always going to appear smaller. It is going to be virtual, meaning it's going to be behind the mirror, and it's going to be upright. Okay. So there's only one for convex. Okay. This is what's always going to happen in convex. So that's all for mirrors. Okay. I don't want to do any math for this because this is that. Firstly, it's weird. It's niche. It's for figuring out where the focal points are and things like that, which isn't all that vital. What is vital though is just knowing how it works, because these are how glasses are made. For those of you that either wear contacts or wear glasses, when you go to the eye doctor and they measure your eyes and they look at all these things, what they're looking for is where the focal point for your eye is. So let me see if I can get a quick image. Okay, Let me see if I can get a quick image that shows you what I'm talking about. Okay, here it is. Perfect. Can I? Okay. So you want the focal point in your eye to be dead center in the back. Okay. But if the focal point is too in front, like you see here, okay, if it's too in front, you get nearsighted. If it's behind, then you get farsighted. What glasses do is they change the focal point so that it's dead center on right smack on the back of your optic nerve. So they make these mirrors or your glasses or the shape, the curvature of the glasses is based off of the focal point. Okay, the adjustment you need is what's going to determine the curvature and the thickness of the glass that you need. Okay, so that's how all of this works. Okay, I'm not worried about the math on this one. So there is no worksheet for today, but it is vital that you know how this stuff works because a lot of people, if you don't wear glasses now, you might in the future. If you don't wear contacts now, you might in the future. Okay, because vision only gets worse as you get older. Okay, so you might need it eventually. And this is how they work. Okay, but that's it for today. There is no worksheet. Today's Tuesday, right? Yes. Happy Tuesday. Take care. Stay safe. Have a good one.